Namaskar. So I start this another part, that is part two. So let me remind you that was what exactly we were discussing in the part one. So part one, I have shown you that the fundamental part of atmospheric physics is related with your hydrostatic um, balancing equation, and I introduced some of new parameters, and now as you know that we can call them Brunt-Väisälä period, and then uh, potential temperature, etc. So these were the different parameters which we have discussed, and I have also introduced you that why atmospheric physics is very important. The dynamics is also very, very important. So let me proceed further, that in the part two, I want to show you that what are the glimpses of some of the findings using satellite. I think let me take a couple of seconds that I introduce you the radar, measurement of the radar. And radar can take observations at a very fine time scale and at a very fine altitude scale. I mean, you can say that after every 2 minutes, you can take observations with time, and you can divide this height at like 75 meter, 150 meter, something like this. It depends. If you want to operate the radar at the lower height, you can have the better height resolution. But if you want to take this signal, you want to throw this signal up to like 80 kilometer, 100 kilometer, 150 kilometer, it can go up to like 250 kilometer or so, then you have to lose this height resolution because you have to increase the power of the signal. And the deeper is the signal, and then lesser will be the resolution. That is the beauty of this. But nevertheless, I think we can say specifically that radar is a very versatile tool, and you can operate this from the lower height up to like 250 or 400 kilometer in order to study about the plasma and all at the higher altitude. But at the lower height, you can study the cloud structure, internal cloud structure, and backscatter radar reflectivity. I think I just take a couple of seconds again. Let me introduce you, because in Delhi, and especially in the northern India, for the last couple of days, there have been very heavy rain. And this rain is unprecedented. It never happened in the month of like September. And we were looking on the news, and then they told us like 46 years of the record. My point is that how do you get all this information? So it is now basically available using Doppler radar, and Doppler radar is a very good tool to study about the depth of the cloud, and you can see from Indira Gandhi Airport, and there is one more radar, and you can see about like 150 kilometer. You can see the structure up to like Meerut city and little more, and then Haryana, then in southern part, and all around Delhi. So that is the beauty of the radar, that you can see the internal structure. High reflectivity means the cloud is more and more dense and more deep. You can see the depth also, of course, and the movement with time. So now you are having the radar, you are having satellite, you are having radio sonde, and you are having many more tools. So by putting them together, you can have the complete information of the weather system. So I introduce you that satellite is very useful in the sense that you can take observations over the oceans and see where it is not possible. Radar, of course, you can operate over the land, but it is difficult that we cannot do that there. So now let me introduce you that what are those fundamental questions for which we are looking for. And I'd like to mention and feel happy that in Rajdhani College, we are having a radio atmospheric physics lab. And that is the only laboratory of Delhi University where we do the atmospheric physics observations, measurements, and we also correlate this with the environmental sciences. We also look for the space activities and number of things we are doing for last 25 years. So let me introduce you that what are those basic questions for which we are working. So this is, of course, the first one is radio sound and rocket observations of the middle atmosphere. And in fact, there was very less information about the middle atmosphere. When I say middle atmosphere, I introduce that from 10-kilometer altitude to 100-kilometer. And because it is a, it's not, it's something like major part of this is unionized. No, and is of course neutral atmosphere. That is the correct word that we can say. Neutral atmosphere and difficult to get back scatter signal. So remote sensing has been very challenging in this area. But after the invention of this VHF, like very high powerful radar system, where you can send the high power signal in the atmosphere, and if you are able to get the fraction of that, very small fraction of that, so that is sufficient to process this data, and you can get information what is happening in the neutral atmosphere. So as I mentioned in my part one, that radar was used earlier to have the like metal object, especially the aircraft, but now the things have changed completely. You can take observations of the atmosphere and you can get backscatter from this change in the refractive index. And that refractive index change is happening in the first 15 kilometer, which is very dominant feature. And as a result, you can get all atmospheric parameters, activities, or temporal variation and with height variation. And then later you can use them in terms of like weather forecasting also. So radio sonde and rocket, they were the basic tools before, but now things have changed. Now satellite has come into picture, and powerful radar, X-band radar, and there are UHF band, ultra high frequency radar. So they are working in addition to the VHF band. Then what are other important questions which were tried? And these are fine scale measurement of atmospheric gravity waves. They are basically induced by convection, and VHF radar can take observations. So these fine scale atmospheric gravity waves, they are like having time period of 10 to 20 minutes or 30 minutes, and it can go up to a few hours. And the horizontal wavelength is about like a few hundred kilometers. Vertical wavelength, I mean, the wave travel like this. It goes making some angle with the horizontal, and then you can divide this into UVW component. So from here, you can estimate that what is the horizontal wavelength and what is the vertical wavelength. And they are basically produced by the thunder. And because it is a fluid system, it's just like a gas. So if something happens, or it is just like a balloon and you bump this, and then it is something like creating kind of the ripples, and they basically propagate in the atmosphere. To detect and to determine these atmospheric gravity waves is very important for us to understand, because they interact with the basic wind in the background. And by the interaction of the basic wind is, I think you can imagine something like you are having a river, and on the top of the river, you are having perturbations. And these perturbations, they are kind of, you can imagine these are waves, and it's a huge water body which is flowing exactly in the atmosphere. You are having a basic wind, and when you go from ground to about 15 kilometers, the wind speed is increasing, and near 12 kilometer wind speed is very high, like 40 meter per second, 30 meter per second or so. So it means if you calculate in terms of like kilometer per hour, it goes up to like 100 kilometers per hour or something like this. So these are the like magnitude. And when in the background, this huge like basic wind is propagating, is blowing, and these interaction, the perturbations, what we call the gravity waves, they basically interact with the background. And when they interact, so they either transfer momentum or energy to the basic wind. Either when you transfer this momentum, there are two possibilities. It may accelerate the basic wind in the background, or it may deaccelerate. It depends if it is going propagating in the same direction as that of the basic wind or in the opposite direction. So this is itself is a very major area, and I think many international groups they have worked, and we also worked on this particular topic. And during this mid 1995, so Ionospheric Research Center was one of the I think prime um, in center for physics department of physics and astrophysics of Delhi University. And Dhaka is a village very close to that, maybe just about 3 kilometers. Um, and there was a huge system we called Ionospheric Research Center, IRC. So there was a huge antenna. So when this antenna is basically injecting power or radiation, and this was basically observed for the ionospheric absorption at around 80 kilometers or something like this. So this was a very specifically designed apparatus. And then, of course, it was installed in mid 60s, and it continued up to like 1997, 98, and then finally they shut down. So we also utilize this equatorial atmosphere radar, and this is basically located at Kota Tabang, Indonesia. And because Indonesia is a country of like having maximum convection system, as a deep convection system. So this radar was installed by the Kyoto University, by the support of Kyoto University and Japan government. And we were the part of that. It was installed in 2002 when I was in Japan. We also utilized this new radar at Shigaraki, Kyoto University, Japan, study of the high frequency gravity waves and afternoon convection. So these were also utilized. So I was talking about a new radar at Shigaraki, Kyoto University. And as I mentioned that this was also very important focused for high frequency gravity waves. In addition to this, the most important or fascinating observations have been of using satellite, and this was used for the lower and the middle atmosphere. I'd like to add here some very important information that the radar has got its limited role in the sense that you can utilize this at a particular station and we can take observations on the land. But there are some area over the globe, especially which is very highly convective. As I mentioned earlier, that maybe Indonesia is one of them, and we cannot understand the structure or the configuration and the time evolution of several atmospheric processes. For that particular part, satellite observations is needed, and you can use those observations to understand the dynamics over oceans and over sea area, especially from Indian point of view, like in the Indian Ocean and Bay of Bengal, Arabian Sea. These are the areas where we have to keep a watch that how the dynamics is changing, how the weather system and thermal structure is changing with time. Then, in addition to this, another important topic has been for the long-term changes and the climate system. This is also, we are looking for association with the solar insolation. I think these topics I'm discussing one by one so that you can really develop some kind of the basic understanding and the idea and a new thinking when you talk about especially the climate system. Because in general, people talk like the temperature is increasing with time, and it is happening because of the CO2 emission, methane emission, water vapors, and maybe other trace gases, which are really important to uh, contribute, and especially the anthropogenic activities for the climate change, or to increase the temperature by like zero point 0.5 degrees centigrade or 1 degree centigrade over a long period of time. But it is very essential to add this information with the solar insolation, because solar cycle has a 11-year period. So after every 11 year, the sun passes through uh, high solar maxima to low solar maxima, and these activities can be seen or can be captured by counting these uh, spot number. There are sunspot numbers. So sunspot activities basically increases after every 11 years. And we have also tried to see this, whether these kind of activities do have influence in the Earth atmospheric lower Earth atmosphere temperature, and up to some extent we can say yes. So after every 11 year, if you are having like maybe 1 degree centigrade change in the temperature, we should not misunderstand that this is happening due to the climate change. Rather, it is a natural variability. So therefore, I have included specifically this point. Then let's also discuss something about PM 2.5 measurement and atmospheric dynamics. And we have taken this particular part, and in collaboration with the international laboratory, especially in Japan, we have got some smart sensors and we are utilizing them. And one or two we have put them at Rajdhani College to tell to our students that how PM 2.5 is changing with the time. Even within 24 hours, every hour it changes, and that is what we call the diurnal variability. And of course, and the last point I'd like to include about the mountain meteorology. So in the mountain, the meteorology or the atmospheric local dynamics is different than the plain. And we have did some, one of my student in fact did experiments at Nainital areas. So that is again fascinating. We are having clear-cut difference in the afternoon formation of circulation pattern, wind circulation, and they are totally different than in the Delhi area. This is, of course, we talk about a plain area meteorology. So, as I mentioned, that these are the basic challenges, how to tackle them, how to measure them. We tried, and in a nutshell, I'd like to mention that some of my PhD students at Rajdhani College, they completed these particular topics. And because, college is a small place comparatively, and to do this kind of like research work is quite challenging. However, we accepted that and we got a small laboratory here with the support of Indian Space Research Organization, and continuously we are contributing. So this topic of study of the gravity wave due to convection using MST radar, this was done by one of my students, and the essentiality I already mentioned. And one student has done for generation mechanism and characteristic of atmospheric gravity waves at Indonesia. We compare with the Indian MST radar at South India, located at near Tirupati. There's a small place we call Gadanki. And then we had tried to understand that how the dynamics at Indonesia is a archipelago, because there are a number of islands surrounded in Indonesia, surrounded by them, and the convection activity in the afternoon is quite high. And then we also compared with this uh, facing this area, Bay of Bengal. So because the radar is exactly very close to that, and we, we 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 got to good results and fascinating results. Then the two more students study of convection induced as atmospheric gravity. This was based on the specific campaign. They were conducted again in Indonesia in 2004 and 2005. Every 3 hours we launched radio sounding, and they were specifically designed, and they went up to like 40 kilometers, and we could find out there's a beautiful uh, dynamics salient features in Indonesia. And solar cycle and tropospheric energetics, this was another good topic, and extensively we have used both satellite and radar, and then to understand the atmosphere and ocean interaction. So we have been quite successful. Then Asian monsoon system, then tropical tropopause area, means how this top of the troposphere, that is what we call the cold point tropopause area, the changes, how they are basically influenced by monsoon is also studied. So the next is the fine scale tropospheric gravity wave. This is again challenging because uh, troposphere, as you know, is a quite turbulent part of atmosphere, and when it is turbulent, and you have to capture those stable time period so that you can see. I think it is important from fluid dynamics point of view. Uh, if the atmosphere is stable, then it will support the propagation of atmospheric gravity waves. And if it is not, then if they are generated, then basically they will dissipate easily, and they will transfer their energy momentum to the background. And then we started using satellite observations, and this is a group of satellite we call Cosmic or Formosat 3. And Vinay Kumar, in fact, he studied extensively this starting from 2006 onwards. So this group of 6 satellites we utilized to understand the thermal structure at a very fine scale, starting from North Pole to the South Pole, all along through the across equator on both hemisphere. And then uh, Anju, she has utilized CO2 emission, and CO2 emission is very important because as already we discussed that we don't know how this contribution is making this climate change. So over the last several years, the CO2 concentration, how it is changing with time. So every year we found it's nearly like 2.01 ppm per year. It is increasing, and you have to stop it. And you know, it's a group of international countries, and they are working in this direction so that you have to cut down CO2 emission in a given time frame. Then meteorology in the mountain area, especially in Himalayas, and relationship with the monsoon and aerosols. So I just would like to show you that the contribution in the different topics, important topics, has been made, and we I think published about like 50 international papers from this small laboratory. So let me come to the actual point, and this is what I want to tell you, that why satellite observations are important. This is, of course, in the last view graph I mentioned that why the different topics they are important, what kind of the study could be carried out, and what are their respective contribution in order to understand about the atmospheric physics and atmospheric chemistry all together. And that this has been a satellite era in the remote sensing. and you could see each and everything everywhere globally. So suppose something happens like in India in terms of like large emission, and this emission goes to atmosphere. So, and you know, globally there are the wind system. It moves from one place to another. Then definitely another country, if you are like on the eastern side or you are on the western side, then naturally the air pollutants, they will travel all along, and the another part of any part of the globe will be affected. Similarly, like something happens in the southern China or the industrial part of China, and then naturally the entire Asian countries would be affected. So there has been a study we call Asian brown cloud, ABC, and these clouds, they were basically created by the industrialization, especially in China. And in India, of course, we are also having rapid industrialization, but we also have to take care about the air pollution. And of course, that is a different topic, that how our health is affected. But first, let us focus that how the satellite observations are important to understand fine scale things from land to sea and ocean, and how they are different with each other. So let me, already I mentioned that what is the objective, what is the motivation. So I show you a group of 6 satellites and how they are utilized, like in the Indian sector, African sector, and all together. And our focus, India is located in the tropical belt. So we have also used the tropical belt. So some of the results I would like to show you with a very specific technique, and this is what we call the radio occultation technique. And this data we have used cosmic data, the constellation observing system for meteorology, ionosphere, and climate. And this was launched as a joint collaboration of Taiwan and America, and it was launched in 2006. So from 2007 onwards, we could get the data and we utilize that. So a quick comparison for this is that occultation, we call radio occultation, is the name. It is something like this is your Earth, and one satellite is in the background behind this, and this is your GPS. So when you send the signal, the Earth is here, but because of the refractivity, it travel all the way and it reaches to this. So signal is basically coming closer to this GPS. But in this process, what is happening? It passes through this atmosphere, and then there is a banding. Banding is happening because of the refractive index changes, and you could observe the entire atmosphere. And I will show you some of the examples. So this cosmic was very unique. 6 satellites already I mentioned, and you can see that there were another satellite launched by Germany, CHEM, and by France. And if you compare, these were the number of observations. So they were about 8 times larger than these two. And now, I think last year in 2019 or 20 already another cosmic 2 launched, and now we are having more satellite so that you can have more observations. And observations for this radio occultation is basically up to 40 kilometers from the ground. From ground means like maybe just 2 kilometers to 40 kilometers. And if you are having these number of like profiles all over the globe, it is really good to understand. So let me show you one example that daily you are having about 2,500 profiles. Let me remind you that if you launch such a radio sonde costs you like 40,000 rupees or so, and it is launched twice every day. and we are having about 40 stations. So this is being done by India Meteorological Department. But you can see from here, this is a globe, and the green dots over the globe, these are the locations where in one day you are having a profile from ground to up to 40 kilometer. And the red dot, these are basically the land area where the stations are there and they are launched from the ground. But you can see from here, means in this particular area, that you are having a good comparison of radio sound launched from the ground and satellite observations. And they were compared, and of course, they were there was a very close agreement of the results. So what was the benefit for this? The benefit was like you were having 500 profiles and 25 profiles, especially like in the polar region. And yes, yeah, you can see from here. So this is your northern hemisphere. In the northern hemisphere, the red dot and the green, they were large in number. So as a good agreement. But the beauty is for the satellite observations were in the Antarctica, because in Antarctica, there were only maybe few stations. They were installed long before, but you can see the green dots, they are in large number, and you can have information in this area about the temperature, how it is changing in the troposphere, how it is changing in the stratosphere, whether there is a difference between the northern hemisphere or the southern hemisphere, and you can utilize this kind of a data. I think this may be partly interesting to you, that this is in a month from 30° north to 30° south, and the entire tropical belt is filled with observations. So these observations is almost covering every part of the globe. And in 1 month, if you operate this, so satellite data will give you the a beautiful picture or snapshot of temperature in this particular band. I think this is very, very interesting figure, and any atmospheric physicist or student or researcher, they should understand it. This is what we call top panel is QBO, quasi-biannual oscillation. Quasi means it's not exactly, and it is quasi is biannual means 2 years, and quasi means it's not exactly 2 years. So it may be little more or maybe little less. So effectively, it is about 28 months. So in the 28 months, there is a oscillation in the atmosphere, and I will explain this, how this oscillation is basically created. It is something you are having time here, 2007, January, 8, 9, 10, 11, 12, 13, and this is your scale. Red is 2 to 4. The dark red is about like 4°, and the medium red is about like 2°. And then blue is minus. And here is your altitude from 0 to 40 kilometer. And just focus your attention here around 20 kilometer. So can you see these? These are the very specific pattern: blue, then red, blue, and red, blue, red, blue. And of course, they are touching this cold point topopause. This is topopause like around 16, 17 kilometer around here. So they are touching this top of the troposphere. That is the first, like these are the coldest point area. Now, just I take a couple of minutes here. The red is warm. This is cold, warm, cold, warm, cold. And these patterns, they are embedded in the stratosphere, starting from 40 kilometer, and there's a downward phase propagation around here, downward phase propagation. Now, how they are basically produced, that is a very complicated question. But at least we can understand this, that the atmosphere oscillate, the 14 months is like is cold, and then 14 months is warm, or getting polar, warm, and this is very alternate, very systematic. And this exactly what we call quasi-biennial oscillation in temperature. But wind pattern, atmospheric wind pattern also shows similar behavior, that you are having eastward, then westward, eastward, westward, same exactly. Even water vapors also show this kind of quasi-binary oscillation. This is very strange that we can understand that there is an annual variability. So we understand it is happening because of the solar annual cycle, that you are having summer, then you are having winter, and then of course, and you can also understand like semi-annual. Semi-annual means like half summer and half like colder part. But what is so specific about 14 months? So they are basically produced by vertically propagating waves, and they interact with the background. As already mentioned, that there is a basic wind in the background, and there are atmospheric waves. So systematically they interact, and they produce this downward propagating downward phase propagation pattern by those, because they basically impart momentum and energy, and they bring down this every time. And because